Okay, so the beauty of this lesson is it's going to feel very familiar to something we did, I think it was last chapter. Now I can't think of what section. 10:6, maybe? 10:4? No, I don't know.
It was the one where we did the area ratio to volume and everything.
Yes. Yep. So going from a scale factor to an area ratio to a volume ratio, right? We're dealing with similarity. So here's the deal. That same idea is going to come into play here. You're working with similar solids. You're working in three-dimensional figures, but dealing with scale factors and area ratios and volume ratios. So it should feel very familiar to you. There's just a few slight differences and add-ons and whatnot. So first thing you gotta think about is what are similar solids. And in order for two figures to be similar, they have to be proportional. Okay, so their heights are proportional, their lengths are proportional, their widths are proportional. Whatever dimensions we have, they are all proportional to each other. Okay. One thing to note is every single cube is proportional to every single other cube. And every single sphere is proportional to every other sphere. There is no way for them to not be proportional. Because if you think about it, like a cube, for instance, all the sides are the same. So if you set up a scale factor, for instance, if this is 2 by 2 by 2, and then you have one that is 5 by 5 by 5, okay, your scale factor is going to be 2 to 5, or 2 to 5, or 2 to 5, right? So every single cube is proportional to every other cube. Same goes for spheres, because your radius is a radius no matter where you put it in a sphere, okay? So those two will always be similar. They will always be proportional to each other. But there are plenty of figures that are not similar. So the first thing we're going to do is just figure out, are these figures similar? Okay, so the question is, are they similar? And I'm going to give you two rectangular prisms right now. So the first one looks like this. Oops. And this is not necessarily drawn to scale. In fact, it's not. Okay, so let's say this first one, we have 3 by 3. This is supposed to be 2. I know it doesn't look like it. And then this one is 6, 6, and 4. Okay, to determine if they are similar, you have to match up the corresponding parts and create a scale factor. So if I'm looking at numbers here, what is one ratio, one scale factor? 3 to 6 would be 1. Okay. 2 to 4 would also be 1. And then the last one? 3 to 6. So you have those 3 ratios for the sides of your figures. Would you say these are similar figures?
Yes.
Why?
Because they're equal.
They are all equal. So if you reduce, and you always need to reduce, guys, every single time, reduce, reduce, reduce. This is 1 to 2, this is 1 to 2, this is 1 to 2. So we would say, are they similar? Yes, they are similar. Because they have the same scale factor. Okay, a scale factor of 1 to 2. So how about these ones? If this is 2, 3, and 2, and this is 3, 6, and 3. Okay. Are they similar?
I doubt it.
What are your, I doubt it too. What are your scale factors?
2 to 3, 3 to 6.
3 to 6, 2 to
You have a 2 to 3, right? 2 to 3.
I said that.
You have a 3 to 6.
I first that.
Great. You have a 2 to 3. Okay. If you simplify that, 2 to 3 does not equal 1 to 2, which does not equal 2 to 3. So the question, are they similar? We would say these are not similar because they don't have the same scale factor. Okay? Questions on that? So that's just, are they not? One thing to think about, excuse me. Thank you. When we talk scale factor, we're talking a relationship between like the heights of the figure or the lengths of the figure or the widths of the figure. So just keep it in mind when we get to a scale factor versus an area ratio versus a volume ratio. Scale factor is dealing with lengths, right? The lengths of the sides. Okay, so let's talk how these ratios relate. If we have a scale factor of A to B, okay? Then if we are going to do a surface area ratio, based on what you know from the last chapter, what do you suppose that ratio should be in terms of A and B?
A to the third, B to the third.
Surface area.
A
A squared, right? So area you're squaring, okay? If we're trying to find a volume ratio for that same figure, then you're gonna cube it. So that's gonna be A cubed to B cubed, okay? So this one gets a little bit trickier now that there's volume involved. Think about it this way. If you are at a volume ratio, how do you get back to here?
You do the cube root.
You cube root it, right? It's the 3 with the square root symbol. You cube root to get to the scale factor so that you can square it to get to here. So sometimes you're going to start with volume, have to cube root it, and then square it to get to area. Other times, you're going to start at area. How would I get from area to volume? You would square root it to get to here and then cube it to get to here. So when you have a problem like that, that goes from surface area to volume or volume to surface area, you will always do two things. You'll either square root and then cube it, or you'll cube root and then square it every time, okay? So just think through this setup. I feel like that's very helpful for you to kind of visualize what needs to happen. So let's say we have, just a quick for instance here, a scale factor of 1 to 2. What's your surface area ratio? 1 to 4. 1 squared to 2 squared is 1 to 4. Okay, what's your volume ratio?
Oh my gosh, 1 to 8.
You're going to cube it. 1 cubed to 2 cubed is 1 to 8. Okay? So just, yeah, understanding the relationship between those. Okay, so here's what we're going to do. I'm going to give you a ratio. Okay, let's say we're going to find the scale factor. If the volume ratio is 3,375 to 1,728. Okay, so that is a volume ratio. How do I get to a scale factor? If I'm at volume, right, if you think up here, we're at volume, we need to get to scale factor. you would cube root it, okay? There's no squaring. We're not trying to get to area. We're just trying to get to scale factor. So if I cube root 3,375 and I cube root 1,728, I get 15 on top. And maybe you want to plug these in just to make sure you're cube rooting correctly. Um, 12 on bottom. Okay. Now, here's my question. It said find the scale factor. What is your scale factor? It's 15 to 12, but that's not the best answer.
Oh, it's
5 to 4. Okay, so make sure you reduce. If we divide both of these by 3, you get 5 to 4. So your scale factor is 5 to 4. Okay, look for places to reduce. You need to reduce for these. Okay, so that's a scale factor, 5 to 4. Questions on that? Okay, so what if I started you with an area ratio and I said find the scale factor? What are you doing?
Just red. Wait, what?
Just the square root, right? You're just taking the square root. So if I start you with a surface area ratio and want to get to scale factor, you just have to square root to get there, okay? All right, example 3.
Example trays.
This says the volumes of two similar solids are 40 cubic inches and 135 cubic inches. If your surface area of the smaller figure is 48 square inches, what is the surface area of the larger figure? And if I could just refresh your memory, this question on the test in chapter 10 was the one that was done wrong the most, where you had to go from surface area and then turn it into, no, not surface area. We weren't talking surface area. You had to go from area to, nope, it wasn't that. Can't remember how that question was worded now. But you had to do like a double step, right? You had to square root and then you had to, it wasn't that way. You had to square in the end. And people didn't square it, okay? So multiple steps here. Don't forget the last step. Don't forget to get to area, okay? So we're starting at volume. That means our volume ratio is just taking those two volumes and making them a ratio. So for a volume ratio, we have 40 to 135. Okay, those are our two volumes. But now here's the deal. We said you have to do what with these before you cube root? You want to reduce, okay? So 40 to 135, you can divide both of those by 5. So that is 8 to 27. And if you notice, when you do that, you get these beautiful numbers that are very easy to cube root, okay? So that is my volume ratio right now. But we want to get to surface area. So in order to get to surface area, this is what I was talking about earlier. If we're at volume, we have been cubed. How do I get to surface area? You cube root it. That gets you to scale factor. And then you do what? Then you square it, okay? So I'm just going to bring you back up here real quick, right? We are currently here.
3 to 1 to 2.
We have volume, right? We're going to cube root it to get to here. So you take the cube root, and then we're gonna square it. That number squared is gonna get us to surface area, okay? Don't forget that squaring step. That's the one that always gets forgotten. So if this is my volume ratio, my scale factor is the cube root of 8 over the cube root of 27. When you cube root 8, what do you get?
You get 2.
2. When you cube root 27, you get 3. Okay, so this right now is my scale factor, but we don't want scale factor. We want the surface area ratio. So what do I have to do to that number?
You have to cube it.
Not cube it. You have to square it. So 2 squared to 3 squared gets you a ratio of 4 to 9. Okay, now here's the deal. That was several steps, but you're not done. Don't stop there. You want to know the surface area of the smaller figure, okay? Keywords here. Sorry, they give you the surface area of the smaller figure. What is the surface area of the larger? So you take that surface area ratio, 4 to 9, and you set up a proportion. Where is that 48 gonna go? On top. It's the smaller, right? So put it across from the smaller, x on bottom, and then you cross multiply that. So it's gonna cross multiply 4x equals 48 times 9 is 432, and then you divide by 4 is 108. 108. And we were talking inches, and this is a surface area, so 108 square inches. They gave it to us in the problem, right here. The smaller figure had an area of 48. So sometimes in the homework, the way they lay it out is this. They'll give you like a volume, and a surface area, and you have to find the last surface area, or they'll give you a surface area, and a volume, and you have to find the last volume. So make sure you're paying attention to what you're doing. If you're here, if you're going surface area, and they give you one volume, you have to square root first, and then you're going to cube it, okay? If you're here, you're gonna cube root first, and then you're gonna square it. Okay, so just be very clear on that, the order that you go in. Okay? All right, last one. And I'm not going to write this one out because it's a lot of words. But it says Office Max sells paper clips in small and large boxes. Okay, so a small box versus a big box of paper clips. The small box holds 220 paper clips. Okay, the large box is formed by doubling the dimensions of the small box. Okay, so the large is double the dimensions.
Then wouldn't it fit double the paper piece?
No, but that's what people want to say. So the question is, how many paper clips will fit in the large box? Now you got to think about this. The number of paper clips in the box is which thing? Scale factor,
Volume.
surface area, or volume? It's volume. It's how much you can fit inside. Okay, so this is a volume right here. But this says you double the dimensions. So you double the height, you double the width, you double the length, right, of the box. So that means that my scale factor is double, so 1 to 2. We're doubling the dimensions. That would be my scale factor. We're looking for what? We're looking for the volume of the bigger box. So my volume ratio is going to be what? 1 cubed to 2 cubed, right? So my volume ratio is 1 to 8. So if I know my volume ratio, 1 to 8, and I know the volume of the smaller box, where is that 220 going to go? On top, across from the smaller number. And then x on bottom, and you're going to cross multiply that. So 220 times 8 is 1760. So we would say the larger box can hold 1,760 paper clips. Okay, questions on that?